Hi, welcome to a fresh module on calculus for AI ML. We are building the foundations for machine learning, and today we are starting with learning calculus. In the previous module, we had looked at linear algebra, statistics, and probability. And here comes the most exciting and personally my favorite part, calculus. This lecture is going to be fairly easy if you are familiar with calculus, especially derivatives and concepts like continuity. So if that is the case, feel free to skip the lecture. No worries. But if you want to stay with me in the lecture and if you already know the concept, consider this as a refresher. Otherwise, if you are learning about calculus for the first time, I'm sure you're going to enjoy. You will enjoy regardless. So in backpropagation in machine learning, neural network models, one of the things that you often use is chain rule. And once I was building a neural network from scratch and I wanted to define the function that dictates the change in weights for every backpropagation event. And I was having a very hard time defining the function in terms of the weights itself and in terms of the input to the neural network, because I had like a softmax activation function at the end of the neural network. So it was a bit tricky to define the partial derivative in that case. So I'm just saying this because the importance of calculus in neural network and in machine learning overall, you will get to appreciate it only once you start doing complex things. Up until that point, you will not feel like you need such a strong hold on calculus. But believe me when I say this, if you have a strong hold on calculus, it will make your life much more easy down the line. So let's start today's lecture with very simple terms. And this lecture is going to be like a cakewalk for you if you are familiar with calculus. So calculus is that branch of mathematics which focuses on accumulation or rate of change. Accumulation is usually calculated using integral calculus, rate of change using differential calculus. And this is very important in optimization algorithms, in backpropagation, everything. Basically, it is one of the mathematical foundation blocks in AI ML. If you have heard of gradient descent, I would say that calculus is probably the most important thing that you have to learn from math to perform gradient descent or even to implement it from scratch. And there is something called adjustment of weights in neural networks. So you start with random weights and you adjust the values of these weights based on how far off your neural network predictions are compared to actual values it is supposed to predict. And the rate at which you or the mathematical logic using which you make these adjustments is using gradient descent and something called as loss function. And here also calculus is used very heavily. So today in this lecture, we are not going to cover the entire calculus because it's very vast and broad. And even in the series of lectures that this module has, I don't think I'll be able to cover the vastness of calculus. But that is not my intention either. My intention is to lay the sort of the basic concepts that you need to be familiar with. So in this lecture, we'll be looking at limit and continuity first, and then we'll be looking at derivatives. So certain rules of derivatives and chain rule where these derivatives are applied, etc. So limit is nothing but the limiting value of a function as the function approaches, as the input to the function approaches a certain number. So if f of x is a function, then as limit, this is the way you read this is as limit x tends to a, f of x equal to L, meaning as x approaches a, the value of the function approaches L. It's not exactly L, it won't be exactly L, but it will be something very close to that. And this is a numerical example. You might find this trivial until the point when you realize that there are discontinuous functions. You will soon see that in a moment. So limit x tends to 2 for f of x, where f of x is x square plus 2x is nothing but 2 square plus 6. It is 10. So as limit x tends to 2, the value of this function approaches 10. It's not exactly 10, although I have written equal to here. It's not exactly 10, but it approaches 10. So this is a numerical limit. You can calculate numerically the limit of a function by substituting values. This is not possible in all cases. Here is a classic example, sin x divided by x. What is limit x tends to 0 sin x divided by x? You might think that, oh, as x tends to 0, the denominator is tending to 0. So it's like a division by 0. So is it like not defined? But then you will also realize that actually sin x is also tending to 0. but both of them are actually not zeros. So what if both of them are very, very, very small numbers that are very close to zero? Then it will become a division of a very small number by another very small number. It can be a finite number, right? And that is exactly what happens in the case of sin x by x. So this is the graph of y equal to sin x by x. And you can see graphically that as x tends to 0, the value of y, which is sin x by x, tends to 1. So this function has this kind of a form where as x is tending to smaller and smaller value 0, it is still, the value of the function sin x by x is still a finite, well-defined value. And there is also a rule called L'Hopital's rule. And when I was studying this for the first time, maybe 15, 16, 17 years back, my teachers used to read this as L'Hospital's rule. So they used to write it. I think you can write it in that way also, but that's how people used to pronounce. But I don't know what is the right pronunciation. I like to pronounce it as L'Hopital's rule. Whatever is your preference, but people used to write it like this, Hospital's rule. I think both writing is the correct, but anyways, the rule itself is what is more important than its pronunciation. It's if limit x tends to a f of x by g of x is the format of a function, then it's equal to limit x tends to a f prime of x divided by g prime of x, where f prime of x is the derivative of f of x with respect to x. G of x is the derivative of g of x. G prime of x is the derivative of g of x with respect to x. Now, in this lecture where I am going to introduce you to derivatives, I'm already talking in that language. So don't worry if you are not familiar with derivative. Basically, what this means is in the particular context of the function sin x by x, limit x tends to 0 sin x by x can also be written as limit x tends to 0. Derivative of sin x is cos x. If you are not familiar with that, don't worry. No need to memorize this or anything. D by dx of sin x is cos x. And derivative of x with respect to x itself is 1. So this will be when you substitute x equal to 0, cosine of 0, which is 1. So this is the L'Hopital's rule. Now, there is something called limit. Limit, which we already saw, but limit can depend on how you are approaching a certain point. So here in the above graph, you saw that whether you are approaching this point from the left or whether you are approaching the point from the right, it does not matter. The value of the function is the same. It is close to 1. However, that need not be the case for many other functions. So example, look at this function. This function has a value of 0 for all negative numbers, and the function has a value of 1 for all positive numbers. So you have right-hand side and left-hand side limit for x equal to 0 here. So limit x tends to 0 plus, meaning you are approaching 0 from positive direction, f of x is 1. But if you are approaching 0 from negative direction, which is limit x tends to 0 minus, it is f of x equal to 0. So these two are right-hand limit and left-hand limit. And they need not be the same in all cases. There is one more concept called continuity of a function. So a function f of x is continuous at x equal to a if limit x tends to a f of x exists. So limit existing is one thing. F of a is defined. Then limit x tends to a from plus direction and minus direction are both the same and they should be equal to f of a. So for example, if I had a function like this, I'm drawing a function which does not probably exist in real life. So let's say my function was something like this, and there is a small gap here, which is, sorry, I enlarged myself. Let me go back. So let's say you have this function and the way it is defined is such that when x equal to, so let's say this is x equal to 1, f of x equal to this guy 2. But when limit x tends to 1 minus, which means you are approaching 1 from negative this direction, it's equal to 1, which is also equal to limit x tends to 1 plus, because when you are approaching from here also, since you are not exactly at x equal to 1, the value is still 1. But the moment when f of x equal to exactly 1 is asked. So f of x equal to 1 equal to 2. So limit, what this means is limit x tends to 1 plus or minus is not equal to f of 1. So in this particular case, the function is not continuous. So f of a has to be defined, limit has to be defined, and limit from both directions should be equal to f of a itself. Now let's look at an example. Let's say f of x equal to x square minus 4 divided by x minus 2. And if we want to calculate limit x tends to 2 f of x, we can use the L'Hopital's rule. We take the derivative of the numerator, which is 2x. If you don't know how to calculate this, I will show you in a moment. And limit derivative of x minus 2 with respect to x is 1. So 2x divided by 1, where x tends to 2. So it's 4 by 1 equal to 4, right? But then f of 2 is not defined because f of 2 is 2 square minus 4, which is 0, divided by 2 minus 2, which is also 0. So f of 2 is not defined in this particular case. But limit x tends to 2, f of x is equal to 4. But the function is not continuous because limit is defined. Limit from both directions are the same, but the function itself is not defined at x equal to 2. So this is an example of discontinuity. Now you might be wondering if this function, you can write it as x plus 2 into x minus 2 as the numerator and divided by x minus 2 as the denominator, and you can cancel these two and say that, oh, f of x is actually x plus 2, which means it's defined all over. But this is not true, because to cancel the numerator and denominator like this, the numerator and denominator, the denominator, they cannot be 0. You cannot cancel 0 and 0. So this cancellation works except for x equal to 2. So that's the reason why the function is discontinuous. Although you might be tempted to say that it looks continuous because you can simplify the function to x plus 2, right? So this is about continuity. Now let's talk about derivatives. So derivative of f, let's say a function f is f of x, with respect to x is nothing but limit delta x tends to 0, f of x plus delta x minus f of x. So this is the difference in the function's value f, given there is a small difference in the value of input x. So in one case, the input is x plus delta x, other case it is x itself, divided by that change in x itself. So this is the derivative of the function f with respect to x. And there are certain key differentiation rules that will be good for you to aware of. This is very helpful when you are actually writing loss function, when you are writing, if you want to hand calculate gradient descent, etc. So d by dx of x raised to n, which is the derivative of x raised to n as a function with respect to x, equal to n x raised to n minus 1. So as an example, d by dx of x cube is 3x square, d by dx of x raised to 5 is 5x raised to 4, etc. This is power rule. Then there is something called sum rule. So d by dx of the sum of two function is sum of derivatives of those functions. So it's equal to d by dx of f of x plus d by dx of g of x, which you can simplify right as f prime of x plus g prime of x. Fairly simple. I don't even want to show this with an example. It's fairly straightforward. There is something called constant multiplication rule. So if you have a constant within the function and if you're taking a derivative of that whole thing, you can bring the constant outside. So d by dx of c times f of x, which is where c is a constant, is c times f prime of x. So d by dx of 5x square is 5 times d by dx of x square, which is, according to the power rule, 2x. So 5 times 2x equal to 10x. Again, fairly straightforward. I don't want to spend too much time here and unnecessarily increase the length of this. Then comes probably the second most important rule, I would say, before the chain rule, which is the product rule. Actually, there is one more rule. The division rule is also there. So d by dx of f of x times g of x is equal to f of x times g prime of x plus g of x times f prime of x, right? So you take the f of x and then take derivative of g. Then, so basically it's nothing but f g prime plus f prime g. Now you can kind of deduce this constant multiplication rule from here itself, because if f was f constant, if f equal to c, then f prime is 0, because rate of change of a constant with respect to anything is 0, which means this term will not exist. So it will simply be f g prime. And if f is a constant, this will be like equal to c g prime. That's what we calculated here, c f prime. Instead of f, we are using g here, that's all. So if f of x is x square and g of x is sin x, then d by dx of x square times sin x is x square times d by dx of sin x, which is cos x, plus sin x times d by dx of x square. D by dx of x square is 2x. 2x times sin x. So this is the product rule. Then comes the quotient rule. I would say after this, it's the chain rule. So chain rule is the most important. Then product rule and quotient rule will be the second most important ones. D by dx of f of x divided by g of x equal to f prime g minus f g prime divided by g square. So I like to write this as d by dx of f by g without writing the x equal to f prime g minus g prime f divided by g square. I like to write it in a simpler way like this. But basically, this is the quotient rule. It's very easy to derive these rules also, but I don't want to do that right now. One way to derive the quotient rule is like this. So for example, d by dx of f divided by g equal to d by dx of f times 1 by g, right? So now what is the product rule? Equal to f times d by dx of 1 by g plus 1 by g times df by dx, right? And this is equal to f times d by dx of g raised to minus 1 plus 1 by g df by dx. Now, what is d by dx of g raised to minus 1? According to power rule, it's minus 1 times g raised to minus 2 dg by dx. So this will be f times minus 1 times g raised to minus 2 times dg by dx plus 1 by g df by dx. Now, if we write this, this is nothing but minus f by g square g prime plus g by g square f prime. I multiply and divide by g. And what is this? This is nothing but f prime g minus g prime f divided by g square. So this is the derivation. It's exactly what I have written here, f prime g minus g prime f divided by g square. So that is the quotient rule. So if we are calculating d by dx of sin x by x, it's nothing but f prime g. So f prime is cos x times g at the bottom is x itself. Then g prime is derivative of x, which is 1, times f is sin x divided by g square, which is x square. So this is the quotient rule. And finally, the star of the lecture, chain rule. You might be wondering, why is this a big deal? You will see that once we come to the optimization part, which is not in today's lecture, but later part of the course. So d by dx of f of g of x is nothing but f prime of g of x times g prime of x. So fairly easy to understand with a numerical example. So d by dx of y, where y equal to 2x cube, is 3 times 2x plus 1 the whole square times d by dx of whatever that is 2. So here, this will be 6 times 2x plus 1 the whole square. Now, let's say we can take maybe one more function. So yeah, so here basically g of x equal to, we can take this function itself, but I just want to show what is the g of x. G of x equal to 2x plus 1 and f of x equal to, let's say, g of x the whole cube. Then here, if we want to calculate d by dx of f of x according to chain rule equal to df by dx. Sorry, not f of x. This is f of g actually. Not f of x. It is f of x, but technically f of g. So it is df by dx times, oh, not df by dx, df by dg, df by dg times dg by dx. So here, this f prime is nothing but equal to, I'll come to this. So df by dg is 3g square times dg by dx is what? 2, because g of x is 2x plus 1. So dg by dx is 2. And what is g square? 2x plus 1 the whole square times 2 equal to 6. times 2x plus 1. So please remember this. Although strictly writing, this is not how people usually write. You write it as partial derivatives, dou f by dou g times dou g by dou x. But we don't want to enter into the details of that right now at the moment. But basically here, if you are writing dou f by dou g, it's actually g is also dependent on x, right? So at the end of the day, you are taking the derivative with respect to x only in this particular case. But if you remember it like this, it's an easier way to memorize it, or it's an easier way to use it when you are trying to implement chain rule. So that is the chain rule. And then we can wind up the lecture with a very simple numerical example. I'm sure the lecture has been too easy for you this time, but don't worry, I'll make it a bit more difficult from the next lecture onwards. But let's calculate this slope of f at x equal to 2. Slope is nothing but rate of change of f with respect to rate of change of the independent variable. So rate of change of f is delta f divided by delta x. So we can do this derivative using the simpler rule, right? So x square means x plus delta x the whole square minus x square divided by delta x, right? This is f of x plus delta x minus f of x divided by delta x at x equal to 2. So how do we write this? X square plus 2x delta x plus delta x square minus x square divided by delta x. And this is equal to x square and x square will get cancelled. 2x delta x divided by delta x plus delta x square divided by delta x equal to 2x plus delta x. Now, we know that x is tending to 2 in this case, or rather x is equal to 2. We want to find it at exactly equal to 2, but delta x is tending to 0, which means if we substitute, this will become 2 by 2 equal to 4. You can also simply calculate it using power rule. Power rule means df by dx equal to 2x raised to 2 minus 1 equal to 2x equal to 2 when x equal to, 4 when x equal to 2. So that is the derivative. Now, optimization, minimization, we have not covered in its strict sense. So I know that we are kind of jumping the gun here, but I guess that's okay. So let's calculate df by dx equal to 2x minus 4. And when df by dx equal to 0, then 2x equal to 4, meaning x equal to 2. So the x equal to 2 has to be the maxima or minima, one of them. Now, how do we know it is maxima or minima? We can calculate d square f by dx square. So d square f by dx square equal to 2, which is greater than 0. So that is a minima. And all of this you can easily visualize. So basically, if you have a minima like this, here df by dx is what? From in this half, the derivative is negative. So derivative is negative. Then here derivative is 0. And here derivative is positive, which means the second derivative, so derivative is going from negative to 0 to positive at a minima, which means second derivative at that exact point of minima is positive, because second derivative on the right hand side is something, you have a higher value of derivative here, lower value of derivative here. So second derivative is a positive value, because derivative itself is increasing in its value as the curve passes through that point. So d square by dx square is 2, which is greater than 0, is showing that it's a minima, and the point at which the function achieves a minima is x equal to 2. But I know that I have not discussed this minima concept in detail in this lecture. I just mentioned this as an exercise to kind of serve as a refresher for people who might already know this. If you are hearing about this for the first time, don't worry, we'll be covering this in detail. But this lecture is coming to an end here. It was a very basic introduction to calculus, nothing fancy, very, very straightforward. I hope this served as a refresher to many of you if you stayed until this lecture. But if you are hearing for the first time, you are in for a a really good time already. So starting from next lecture, we'll be moving on to a bit of advanced concepts. So thank you so much for starting. We will continue with learning calculus for machine learning in the upcoming lectures as well. I am also very, very excited to cover this module. So take care and see you again in the next lecture. Bye.